share your screen?
Yes. Yes, I hope everyone can see my
Yes,
screen.
we can see your screen. Yes. And even now, all right. So we are ready to go. I'll do a brief introduction. Hi, Mayur. Thank you for joining us. So Mayur Naik has started his work sort of in his PhD times on static analysis, and he was a pioneer in applying machine learning to that field of formal methods, or making static analysis better. But then later he started applying sort of machine learning, deep learning to program synthesis, and this will be the subject of today's talk. Thank you for joining us. I understood that you just came from your class. I'm glad you could find time to join us.
Yes, thanks, Ras. It's a pleasure to be here. So I'll be talking about our experience applying machine learning, and more specifically, deep learning to program synthesis. This is joint work with many folks over the last 3 years. And I'll be touching upon some works more than others. I've just listed all the main authors in this collaboration. Okay, so let me begin with a brief background. So the kind of synthesis framework that I'll be focusing on throughout this talk is called CGIS, so counterexample guided inductive synthesis, um, which began, in fact, with Ras and his PhD student Armando at that time. So in this framework, you have two components, a synthesizer and a verifier. So the synthesizer takes a high-level specification of the program you'd like to synthesize, and produces sequence candidate programs, which a verifier confirms as either the desired program or gives feedback in the form of, say, counterexamples. So in this framework, we can express a variety of different synthesis tasks. And I'm only going to talk about the tasks here that we have applied our methodology to. So we'll begin with loop invariant generation. So in this case, the specification is a verification condition, a logic formula which encodes the program that you see here on the left, along with the assertion. And the goal of the synthesizer is to come up with an expression like the one you see at the bottom left, using a syntactic specification, which is shown at the top right. So that's the grammar of invariants that we'd like to synthesize. And the verifier can be an SMT solver, such as Z3. Okay. Another example is constraint solving. So in this case, you have a different formulation of the same problem I showed on the previous slide, except that now instead of a SMT solver, we might want to use a CHC solver. And the input looks very different this time. It is still a verification condition, but now these are all Horn constraints. And the output grammar is still the same. And here's an example output which a CHC solver like Spacer would accept as a candidate for the predicate ITP that you see here. So ITP is a binary relation over integers. And the goal is to synthesize a program that conforms to this grammar. And furthermore, that a CHC solver can conclude makes this formula valid. Okay. So yet another application, and the one which I'll focus primarily throughout this talk, comes from the AI domain. It's called referring expression generation. It was originally proposed in 2014 by the paper I've listed at the bottom, titled Refer It Game. And the idea here is that it is too challenging for today's AI architectures to describe, let's say, a scene. And so there's a simpler challenge, which is if we refer to a certain object in the scene, at least then can we name that object. So it's a more local task. And then the task was further simplified by folks at Stanford who designed the Clever data set that some of you might have heard of, where to further reduce the noise, they went from real world images to synthetic images like the one you see here. Nevertheless, this is still a very challenging task, even though you see only synthetic objects in this scene, and the goal is to uniquely identify a particular object, in this case, the object labeled G. The reason this task can be very challenging is you might need logical reasoning in order to come up with an expression that uniquely names this target object. So here the specification is you're given an image along with a desired output, which is the object that is labeled, in this case G. You're given a grammar for the program we'd like to synthesize. In this case, it is a conjunction of clauses of the form you see here. You can, for example, talk about the colors of objects or their shapes or their materials and their relative positions and so on. And in this case, the verifier can be something like a data log solver, where you can execute these relational programs and check whether they produce the desired object as the value of a distinguished variable, which I'll call var0. Okay. So in summary, here the goal is come up with a single rule data log program which, when evaluated on a relational representation of objects in this image, will produce a single object as the value of var0, and that object should be the one that is labeled in the specification, in this case G. Okay. So what is the problem with applying conventional search techniques, right? And I've listed a few of them here, the main ones. The syntax guided enumeration, where you can enumerate these candidate programs according to the syntax of the programs to be synthesized. A classic example is eSolver. There are other approaches. For example, there's an approach that we have dubbed example guided enumeration, and you already see some instantiations in the literature, such as FlashFill and FlashRelate, which look for patterns in the input data in order to guess the candidate programs. We have a paper coming up at PLDI called Example Guided Synthesis, EGS, which shows how to, for example, generate relational programs like SQL queries using this idea as well. And then there's evolutionary or stochastic and genetic algorithms, examples being Stoke, which is a super optimizer for optimizing small pieces of code into assembly. There are many optimizations in the literature to speed up this search. I've listed some of them here, such as indistinguishability, which is used in eSolver. This work on probabilistic models to prioritize the search based on likelihood of the programs, and so on. So we set out to understand what are some desirable features of a search technique that we'd like to have. And we came up with these 5 features. The first is it should be easy to design, tune, or extend the search algorithm, right? For example, we should be able to go from a linear invariant generator to a non-linear invariant one by simply changing the grammar of the programs, of the invariants. Right? Another desirable feature, of course, is scalability. Yet another, which is somewhat overlooked in the literature, is that the programs should be natural, or they should have some measure of quality. Okay. And I can give an example here. If you look at the software verification competition, it is acceptable, or even the SIGUS competition, for example. It's okay to produce programs that are very unnatural as long as they satisfy the verifier. Um, um, Furthermore, the last two are very relevant to machine learning, which is we want the search to become smarter over time across different instances. And also a related aspect is we would like it to be able to adapt um, its search strategy to new instances. Okay, so learning across different instances means avoiding mistakes from the past, and it might be that new instances could be very different from those you have seen in the past, and so we'd like the search to adapt itself to them. Okay. So we can look at what has been done in machine learning, in particular in reinforcement learning. So there have been a lot of successes in the context of strategy game playing. So you've heard of, for example, AlphaGo and so on, for chess, Go, and many other games. Right. In this case, however, the rules for strategy games are fairly simple, and the environment gives scores based on the outcome of applying these rules. Whereas in program synthesis, we are given a syntactic specification, which is the grammar of the program to be synthesized, and a semantic specification, which is a verifier, such as Z3 or spacer or a data log solver, as I just showed. Okay. So these differences pose new challenges, both in terms of how to represent a given program synthesis instance, and in terms of how to conduct the search. Okay. So in particular, if you think about the state that you'd like to represent, in the case of games, it is typically a 2D matrix of raw pixels. And the neural architectures are well known, for example, convolutional networks and so on. But for programs, there's much richer structure. And one might wonder what is the best neural architecture. And we have come up with one, which is called graph neural networks. That was discovered by others in the past. So we have just applied graph neural networks to this problem. But there are many other architectures, as I'll talk about later. For example, transformer models, viewing a program as a set of paths and so on, that are also relevant here. There are also challenges in terms of reinforcement learning. So for games, the space of actions is fixed and finite. And there is often a smooth reward that you can come up with in order to learn the policy efficiently. Whereas for programs, you have a context-free grammar to guide the search. and the reward can be extremely sparse. So typically a solver will only say yes or no when a candidate program is proposed. Okay, it typically has more information, but you converting that into a smooth reward is can be challenging. Okay. So here's an approach that we have come up with, and in fact, we have uh, infrastructure that is open source that you can use to cast your favorite problem in this setting as well. Um, so the idea here is to provide a way to represent your specification symbolically, and that becomes the state. Then we have a neural network, which is the synthesizer that will perform a series of actions and thereby producing a series of partial programs that can be executed by the environment, in this case, a verifier. And what we do next is we both update the state and we give a reward to the neural network, and the process repeats. Okay, so if you squint at this figure, you will see the CGIS loop over here. Okay. So what I'm going to do is take a short detour from my slides and show you a demo before proceeding further. So you can go to this website, code2inf.org, and try out some of these examples. Let me pick one of them here. So you see, this is a program like the one I showed earlier. It is converted into this task. So here's the specification, a verification condition. And here's the grammar of the loop invariants we'd like to generate. And what we do is we convert this verification condition into a graph, because we are going to need this symbolic representation for our reinforcement learning framework. So this is again for the user to design. Okay, so we have come up with a particular way to encode VCs into graphs, and I'll talk about more about that shortly. And with these inputs, you can run the framework, and it's starting from scratch here with all the weights untrained. And what you'll see after a while is a candidate invariant. You might say that this is unnatural in many ways, but this is purely because of certain limitations that are very easy to do post-processing or regularizing and so on. And what you've seen here is the number of iterations of the CGIS loop. So there were 17 calls to the verifier in this case. And you can also see a larger number of tests for the pre and post condition checks and the inductive invariant check. And what you see here is the result of partial programs being generated. So in this, even though there were only 17 iterations of the CGIS loop, there were many more checks of partial programs that were needed to get a smooth reward. Okay. You can also use the same framework for, in this case, I'm showing you CHC formulae. And here's the graph encoding this time. It's different than what I showed earlier. The grammar is still the same, but you could use a different grammar if you wanted. And in this case now, once again, the framework is running, but using a CHC solver instead of an SMT solver. Okay. And hopefully it will converge soon enough before I return to my slides. Please feel free to ask any questions while we let it finish. Okay, so here we have the final expression. In this case, Z3 happens to have a CHC solver as well. So there were 9 calls made. Um, so anyway, the framework is general enough. What I showed you, in fact, was exactly the same underlying neural architecture in both of these cases. Um, and that goes back to one of the nice things about this approach, which is it's very easy to adapt it to different tasks without having to provide any hand engineered heuristics and so on. So in the rest of my talk, I'm just going to go over one particular example, which is the refer it example. Let us start with the symbolic representation, right? So how do we provide this representation? I'm going to skip some of this in the interest of time. The point here is we want to go from this rich structured representation of programs to an embedding, right, a vector of reals. And as I said earlier, we use a graph neural network for this purpose. Okay, I won't have time to go into what graph neural networks are, but the idea intuitively is that there's the embedding here is essentially some combination of the embeddings of the nodes in the graph, and those node embeddings are computed by message passing. So there are features about the node itself, but then the more you iterate over this embedding, each node now has information about the nodes farther and farther away from it in the graph. So it has more and more context information. Since we did this work, there has been the emergence of transformer models. So what I said here is not necessarily true today. And in fact, we ourselves are working with not just graph neural networks, but also trying out these sequential models, the transformer models. And there's work between these two extremes as well. So instead of treating programs as a sequence of tokens or as a graph, you can have representations which treat programs as a set of paths. For example, a lot of work by Eran Yahav falls in that category. And there are interesting trade-offs in these different representations. Okay. But all of this work is all about graph neural networks. Okay. In the case of the refer it problem, the representation is relatively simpler. Once again, you see the objects in the scene being represented by various nodes, and there are types of these nodes, along with nodes for their attributes and relationships between them and so on. Okay, so I'm not going to go too much into the detail, but this is one of the limitations of this approach, which is you still have to design the symbolic representation. But once you have that, much of the architecture is automated, right? And I'm just going to show a run of this loop next. So the goal of the neural network at each step is to select an action in this grammar, right? So pick a production rule. In the case of the refer it problem, it is to pick clauses, right? And they are picked according to the representation of the specification and the grammar that is given. So both the semantic and the syntactic parts of the task. And let us say the first clause picked is that the target object should be a gray colored object. Okay, so this is a candidate program that is generated. We then execute this program using the verifier. There are many ways to design the reward, and this is the only other part that needs to be manually designed besides the symbolic representation. In this case, it turned out to be that a very sparse reward is good enough. We did try richer, smoother rewards, but they didn't give much benefit over the simple approach where if the target variable 0, denotes exactly the object of interest, in this case G, then 1, otherwise 0. So in this particular case, we get zero reward because var zero denotes every gray object in this scene. And you can see that there's C, H, and G, right? So what we do next is we update the state based on the output of the current program. So var zero now points to C, H, or G. Okay. So one thing you notice here is that by representing the state in this manner, we are capturing an infinite set of different programs that all evaluate var zero to these three objects. Okay. And the same holds for var1 and var2 and so on, which I'm not showing here. Okay. And then we simply repeat. So the next clause is that var0 is in front of var1. And then the next clause is that var1 is a brown object, right? And at that point, we have gotten a reward of 1 because var0 points to the unique desired object G. Okay. So we evaluated this approach on the clever data set, which I mentioned earlier. And we also created a diagnostic data set, which is even more complex in terms of reasoning. I've shown two such examples here. The first class is 31111, which means that we have 7 objects, out of which 3 are of the same kind, in this case, A, B, and G. And then there's a different kind of object for each of the remaining 4. And the 6-1 category is even harder. You see 6 out of the 7 objects are of the same kind, and only 1 is different. And what is hard about these compared to clever is that it can take fairly complex programs to be synthesized in order to uniquely label, designate a certain desired object. Okay. So here's a qualitative result. In this case, we are looking at the category 31111, where A, B, and C are 3 objects of the same kind, and D, E, F, G are all different. And turns out that if you want to uniquely refer to the object A here, then you need a 10-clause program. Okay, and what is that program saying? It is saying that the object being referred to is the large blue cube to the left of a large rubber blue cube. Okay, and the reason to say that this is a rubber cube is because at the other extreme G is a metal cube. Okay, so these are fairly challenging tasks, and you can think of them as in 2 different categories. The first 3, which is 31111, 4111, and 511, are relatively easier than the remaining 3, 61, 52, and 43. And indeed, you see that our approach does fairly well. It can, within the timeout of 200 rollouts, it can solve the vast majority of these, although it does suffer a bit for these 3 harder categories. But you see that other approaches do much worse. So for example, an enumerative synthesis approach does fairly poorly on these 3 categories, and even not so well on the first 3. Metal is our own prior work, which uses exactly the same architecture that I showed you, but with lesser domain-specific optimizations. And while that does better than the hand-engineered enumerative synthesis, it still doesn't come close to the approach that I presented. Okay, so with that, I'm done. I'll just talk about 3 future challenges here for those of you interested in learning from the lessons that we obtained. The first, I believe, is in order for this approach to become really practical, we need a tighter integration between the neural synthesizer and a symbolic solver. So for example, let's work on differentiable SAT solvers and so on. We are ourselves working on differentiable data log and so on. And so this would enable the approach to be even more efficient instead of using the symbolic solver just as a black box. Another thing that we failed to do despite trying hard is it seems to be a waste to not use hand engineered heuristics that work well for existing symbolic solvers. For example, the indistinguishability optimization from eSolver. We were not able to incorporate this into our neural architecture, but this is worth trying in future. And lastly, there are two parts here which are not so systematic, which is how to design the symbolic representation and the reward mechanism. And I believe program synthesis itself has a role to play in these two aspects. Okay, so with that, I'll stop and I'll be happy to take any questions.
Thank you, Mayur. Let's say we do have time for one question if we want to finish more or less on time. Ramin, would you like?
Yeah, I have a question. Thank you so much for the great talk. So what's your take on the, I was wondering, like the work of Josh Tenenbaum of Clever 2. Have you guys looked into those kind of video processing with this approach?
No, we haven't.
Yeah, because, you know, like I think it's called Cleverer 2. And this is like very similar kind of symbolic reasoning, while, for example, an object is moving inside an environment, right?
Okay.
So I was wondering, like, would this technique, like, can you extend this technique to those kind of scenarios, like symbolic reasoning?
Yes, so this is something we are working on currently, okay, which is allowing the user to express more knowledge using symbolic constraints, but then determining but keeping them in a logic that is amenable to automatic differentiation. So we are currently doing this for a logic called data log, which allows recursion, but then doesn't have sort of some of the fancier aspects of, say, SMT solvers.
Cool.
So yes, that is something we would like to get to eventually, but we are not there yet.
Great, thank you.
Thank you, Mayur, again. And with that, we'd like to switch to our last but not least speaker, Kevin Ellis. And Mayur nicely